Okay, everyone, so we're going to look today at balancing chemical equations or chemical reactions. So last lesson we looked at how to convert from the word equation to the chemical equation with the formulas, and now we're going to review on how to balance. So again, this is a grade 10 topic, but we're going to review our concept for today because obviously this is a major piece that will be for the rest of your chemistry days. So where the idea of writing out balanced equations come from is actually from Dalton's original idea with the law of conservation of mass. So meaning that atoms are not created or destroyed in regular ordinary chemical reactions. So what that means is the total mass of whatever you start your reaction with has to equal the total mass of what you finish the reaction with. So the total mass of the reactants has to equal the total mass of the products. So what that means is essentially whatever components you start your process with, you have to end up with the same components. So all atoms that are on the reactant side should also be on the product side, and of course in equal numbers. So you shouldn't have atoms of carbon all of a sudden disappearing, and you shouldn't really have atoms that are all of a sudden coming out of nowhere. Every element, every atom should be accounted for, because in real life, atoms don't just disappear or appear out of nowhere. And we want to represent that as best as possible. So here are some basically guidelines to go through when you are balancing. So what I would recommend is, and I have this down here as a helpful reminder, is you create kind of an inventory of atoms. So what we're going to do with all our examples today, we're going to count out how many of each element we have on either side of the equation. And then we're going to essentially add coefficients in to make sure that we have the same numbers. So you want to always check elements that are not oxygen and not hydrogen first. So if you have silver or copper or nitrogen, anything else, you want to leave oxygen and hydrogen for the end. Okay, so once we balance out those, we're going to balance out our hydrogens, then oxygens, and then we're going to do a final check. Okay, but it's important, let's say I have water. If I want to change the number of hydrogens, I cannot do this and say, okay, I'm going to change the hydrogen number down here because I need 2 more hydrogens. What you have to do is you add coefficients to the front of your structure. So if I have H2O and I need 4 hydrogens, I have to add the coefficient, which is a big number in front of our molecule formula. So what that means, just to remind you, this 2 applies not only to the hydrogen, but also to the oxygen. So when you add a coefficient, you're changing every element that is with that molecule. So this would now be 4 hydrogens and 2 oxygens. Okay, so let's start taking a look. So here we have a simple reaction just to kind of start us off here. So we have copper and silver chloride, copper 2 chloride, and silver. So this is what I mean by a chemical inventory, just to kind of get you started. So we have copper, we have silver, and we have chlorine. And what we're going to do is we're going to count how many we have of each on either side. I didn't do a really great job at making this table, but copper, remember, if there is no number, that's assuming it's a 1. On this side, copper, there's 1 copper. Silver, we have 1 silver. Here we have 1 silver. But for chlorine, we have 1 on this side and 2 on the product side. So of course, you're going to kind of go down the list. So there's no oxygen and hydrogen here. So we're just going to work with what we have. So chlorine, we can see we need another chlorine on the reactant side. So remember, you cannot just add a number here to the bottom. You have to add a big number in front. So what that does is this changes a chlorine to 2, but it also changes silver to 2. So then you're going to come back over here and say, okay, well, now we need 2 silver. Once you have all of your atoms that are balanced, you have the same number on either side, you are done. Okay, so sometimes you may find you have to go back and forth a few times because it depends on what molecules you're working with, right? So just like here, it changed up. My silver was fine before, but because I changed that number, it's also going to affect other elements. So just be mindful of that. So let's look at another example here. So this one's a little bit more complex, and that's why I wanted to do a simpler one to start. So here we have nitrogen and hydrogen. So we have ammonia reacting with oxygen to make nitrogen monoxide and water. Okay, so what we're going to do is count out how many we have on either side. So this is what we did before, right? So we have 1 nitrogen, we have 3 hydrogens, we have 2 oxygens. On the product side, we have 1 nitrogen, we have 2 hydrogens, and we have 2 oxygens. So notice, if you have an element that's in more than one spot, as long as if they're on the same side of the arrow, you should be adding them up. So let's look at our numbers. So nitrogens were okay, hydrogens were not, and oxygens were not. So we always do so first nitrogen, then hydrogen, and oxygen is always at the end. All right, so we have 1 nitrogen, 3 hydrogens, 2 oxygens, 1 nitrogen, 2 hydrogens, and we have a total of 2 oxygens from the same side. So let's look at what's going to happen here. So nitrogen is fine. Hydrogen, we need the lowest common multiple. We have 3 and 2, which means we need to make them 6 each. So we're going to put a 2 in front of this NH3, but that does a couple of things. That changes our hydrogen, which is what we want to change, but it also impacts our nitrogen. Do you see that? So let's continue on. We'll focus on the hydrogens because that's kind of what we started working on. And here we need to make this 6, so we're going to change a 3 in front of our water. When we do that, that also changes up our oxygen count. So right now we have 1 plus 3, we have 4 oxygens. Okay, so hydrogen is okay right now, but let's look at our nitrogens. We have 2 versus 1. So that means we have to put a 2 in front of our NO to make our nitrogen number 2. But our oxygens also change. This is what I mean by you have to kind of go back and forth. So 2 oxygens plus 3. So we have a total of 5 oxygens that we have on the product side. So now we have nitrogens are fine, hydrogens are fine, and oxygen, we have 5 of them. Now this is where, the reason why I said this is a little bit more complex is because we need 5 oxygens, but the oxygens come as groups of 2. 5 does not go into the number 2, right? So what has to happen here is when you get stuck like this, so if you're trying to put an odd number into oxygen, like this case, we're putting a 5, what you should do is basically double up everything. So what I mean by that is this would become a 4, this would become a 4, this would become a 6. So what that will then do is you kept the ratio the same, but now our oxygens are going to be an even number. So check it out. So we have 4 oxygens plus 6 oxygens, which is 10 oxygens, which now goes into 2. Okay, so when do we do this? When do we have to do the doubling up? It's any time you're trying to put an odd number for the number of oxygens, because 5 is not divisible by 2. The same thing would happen if you had any odd number, 11, 13, 9, 7, right? 3. You can't put that in a divisible number of 2. So what you would do in that case is you would double up all of your coefficients and then adjust your oxygen number. So this is why, remember that one of the rules was we leave oxygen for last. And that's actually the main reason why, is because oxygen sometimes is going to be a weird one where you'll have to do some adjusting to get them to be whole numbers. Okay. So we'll do another example, and then I'm going to have you try some out. We'll pause the video and see how you do. So here's one that involves polyatomic ions. So we have aluminum plus sulfuric acid, aluminum sulfate, and hydrogen gas. So if we were to look at all of the elements, we have aluminum and we have hydrogen, but we also have sulfate. Okay, so this is my helpful hint for you. So you don't have to do this, but I find that it helps a lot for counting. So do you notice how SO4 is on the left side and SO4 is on the right side? So what that means is you can count SO4 as being one thing, right? We're counting the number of sulfates. So in this case, because it's on both sides, we can do that. If you had SO4 on one side, but the other side had sulfur and oxygens in different spots, you wouldn't be able to do this trick. It's not really a trick. It's more like of a hint or a helper. But in this case, because they're on both sides, we're going to keep them together. It's just going to make counting so much easier. And then we have hydrogen. So aluminum, we have 1 on the reactant side, 2 on the product side. SO4, we have 1 on the reactant side, and we have 3, see this little subscript 3 on the product side. And then we have for hydrogen, 2 on the reactant side and 2 on the product side. Okay, so first thing, aluminum needs a coefficient of 2. Right, we can see there's 2 and 2. Sulfate, we need 3 on the reactant side. So we're going to put a big 3 here. So that's going to change our sulfate number to 3, but that's also going to change our hydrogen number to 6. So we have 2, 2, 3, 3. So for our hydrogens, the last piece to this is we want the hydrogen number to be 6. So we can add a big number 3 in front and make that 6. So now everything is balanced. And you can always do a check, like recount your elements on both sides to see if they are the same. Okay, so here's another example that uses the that oxygen odd number rule. So anytime you have an odd number that is going into an oxygen, you're going to multiply all your coefficients by 2. So actually pause the video and give this one a try. You can create your little chemical inventory. So we have carbon, hydrogen, oxygen, and let's see how you do. Okay, so you should have 2 and 1 for carbon, hydrogen 2 and 2, oxygen 2 and 2 plus 1, 3. Okay, so first thing, carbon, we put a 2 here. So that changes our carbon, and oxygen now is 2 plus 1, which is 5. Hydrogen is actually already okay. So here's a case. We have an odd number that we're trying to put into oxygen. So what we do is we double up everything. So this is going to become a 2. This is going to become a 4. This is going to become a 2. So what that now does is oxygens are 4 times 2, which is 8. Plus 2, which is 10, which means now we can put a 5 here. So anytime you have an odd number going into a diatomic molecule, usually it's going to be oxygen, you have to double up everything so you have a number that will be divisible by 2. Okay, so we'll try one more. Okay, so give this a shot. Try pausing the video and balancing this out. Okay, so here we have carbon, hydrogen, oxygen. So we have 4 and 1, we have 10, and then we have 2, and here we have 2, and we have 3. So carbon, you should have 4, which makes then oxygen, we have 8 plus 1, so 9. And then hydrogens, we need to have a 5 here for 10. So this makes 8 plus 5, which is 13 oxygens. So now you're going to double up everything and put a 13 right here. Okay, So balancing these types are more difficult, but once you get the hang of it, it becomes much easier.